should take it slow.
Okay, hello again everyone, and today we'll be going further into integration. We'll be talking about definite integrals and find the area under a curve as well as volume of solid revolution. So here we go. So of course last video we talked about integration with this symbol right here. We're now going to talk about definite integration, wherein we have an upper and lower limit. And what happens is that when you do definite integration, you do not get a plus c because you're not finding a constant. Now this is mainly used to find the area under a curve. And what you do with this is that it's simply the integral of f of x, or more like the integral of f of b. So replacing the x with b minus the integral of f of a. So let's draw out the small graph here, and let's have our curve. Now let's say this is the curve of x squared plus 2, and we wanted to find the area under this curve between the points x equal 1 and the point x equals 5. So I want to find this small area in here. Now of course we can't just use regular method to find the shape because it's in a regular shape. So you have to use definite integration. So what we would do is we would write this as the integral from 5 to 1 of x squared plus 2 dx. And so we'll go ahead and just integrate this. So the integral of this would be x cubed. So you integrate first x cubed over 3 plus 2x. So you integrate first. Now you're going to find f of b minus f of a. So we're going to find f of 5. Let this equal f of x. Now we're going to find f of 5 minus f of 1. So we're going to say 5 cubed over 3 plus 2 times 5 and all of that minus 1 cubed over 3 plus 2 times 1. And of course for this we would just simplify this, put in a calculator and get the answer, and that would be the area underneath this shape in units squared, with a centimeter squared, meter squared, unit squared. So that's how you find the area underneath a curve for that. And you can also apply this a lot in physics. If you remember, let's say we have a graph of velocity versus time, and look something like this, v there, t there. As you know, the integral of velocity, the area under the curve for a velocity time graph is displacement. So the way we get the displacement for a velocity time graph where it's not a straight line is that we would just find the area underneath the curve by using integration. Now let's move on to volume of solid revolution. Now, let's draw another small graph here. Hold on. Okay. Alright, so I have a graph here, y-axis, x-axis, and let's say we have this curve here. Let's mark the limit off right here. And we want to know the volume if this entire curve was rotated about the x-axis. So if we brought it down around the x-axis and came all the way back around, what would be the volume generated? Now for that, it's a very simple formula. Pi times the definite integral, we'll call this point B and the point of the here A. So it's the pi times the definite integral from B to A of y squared dx. Maybe we're asking, why do we have dx with y squared? See, what will happen is, let's say we have the curve of y equals x plus 1. In order to find y squared, if we square y, then we would have to square this side. So we'll square this one, this side, and we'll say that y squared is equal to x squared plus 2x plus 1. And so we can now replace y squared with this, and so we'll get the volume generated if we rotate it about x-axis. Now, just as we can rotate about the x-axis, we can also rotate about the y-axis. Let's say we have a function that represents a semicircle on the y-axis, and we want to know the volume generated if we rotated it about the y-axis. So we'll call this point C, and we'll call this point D. So similarly, it's the definite integral, well, pi times the definite integral from D to C times x squared dy, and as you can imagine, you would simply just find x squared is and replace it with the y function. So if we have a function that says y equals x plus 6, we would rewrite it as x equals y minus 6, and then say x squared is equal to y squared minus 12y plus 36. And of course, we will just replace it there, and that's how you get the volume of solid revolution. Now, these are the two most important uses of integration, especially in the field of physics. Let's say, for example, if we had a graph of pressure versus volume, and the curve looks something like this, and we need to find the area underneath this curve for an isothermal process, we would go ahead and use integration. So yes, it's very important in both economics and physics. Now let's move on to some very special integrals. Firstly, we have the integral of 1 upon x dx. Now, of course, most people, when they see this, would just rewrite this as the integral of x to the negative 1 dx and do it like we do a regular integral. But that's simply wrong, and you realize it because if you do this, then when you raise the power, you'll end up with x to the 0 plus c, which is just 1, and that makes no sense. The truth is that the integral of x to the negative 1 is actually ln x. Actually ln x, and we'll prove this in another video on integration. So this is a special integral which you must pay attention to. Another special integral, the integral of ax plus b to the n. Now you're gonna wanna memorize this one because it doesn't always show up on formula sheets, but it can be very important. And if you don't remember the formula, then doing it from scratch by expanding can be very tedious. So the formula here is just 1 upon a multiplied by ax plus b to the n plus 1 all over n plus 1. Very simple, very easy to remember. Now let's move on to a few others. Next very important integral, and this applies mostly to Unit 2 for students. This one is f prime of x, the integral of f prime of x over f of x is equal to ln f of x plus c. So in other words, if you have a function wherein the top is the derivative of the bottom, then you can apply this general form here. Let's say we have the integral of 2x over x squared plus 2. Now, of course, you know that if you differentiate x squared plus 2, you'll get 2x. So, we can now apply this general form and say that it is equal to ln x squared plus 2 plus c, of course. Now let's move on to another one. If we have the integral of a to the x dx integral of a to the x dx, this is equal to this is equivalent to a to the x over ln a, and we'll also prove this in another video. Now, of course, you can't forget the plus c. Now, of course, our final special integral for this video is the integral of f prime of f of x multiplied by f of x to the n is equivalent to f of x to the n plus 1 all over n plus 1. And of course, you have to remember the plus c. Now, basically, this is similar to the division version, wherein if we have, so this is for if we have the function raised to power and the differential of that function. So let's say we have cos x multiplied by sine to the fourth x, then we will simply apply this because the differential of sine is cos, and we have sine raised to the power. I will just apply this formula. Those are our special integrals for today. In a later video, I will cover how to do integration of trigonometric functions, as well as integration by parts and by partial fractions. Thanks for watching. See you next time.
Tell me pretty lies, look me in the face. Tell me that you love me, even if it's fake.